algebraically. We talked about how to do that yesterday, right? And you guys even saw how you could, if you wanted to, you could even do larger linear systems algebraically by collapsing a 3x3 or by a 4x4 into a 3x3, which you would solve by collapsing it into a 2x2 using elimination, and then work your way out from there, right? So we'll learn that, we'll practice that, and then I'm going to show you a trick for solving large systems using technology that's really quick and easy, okay? All right, so let's start off with, quick reminder about how we categorize solutions. So think what this means. Every system of any size is either consistent or inconsistent. It has to be one or the other. Consistent just means it has one or more solutions. Okay, so there is at least one intersection. Okay. Inconsistent means no solutions. There are no intersections of the graphs. It's also either dependent or independent. Dependent means the equation, there's an overlap, right? So the equations, you get more than just a single point. The example with two lines would be if you had two lines that overlapped completely, those are dependent, that's a dependent system, right? Because they're the same equation. Make sense? Okay, independent means different equations. So how could you get a dependent system with planes, for example, in a 3x3 system? Well, that would be where the planes overlapped, right? Does that make sense? Okay, so we get, those are the different ways that we can categorize solutions. Let's go through an example, okay? And here's the steps, right? So we have to choose some pattern where we would be able to easily get rid of the same variable by using two different pairs of equations and elimination, okay? So like x would be kind of tough. I mean, it would be tough, but it would involve a lot of multiplication of numbers. I'd get really big coefficients probably. Because if I want to eliminate x from the first two, I have to multiply both equations by something. And if I want to eliminate x from any other combination of equations, I also have to multiply it twice, right, to eliminate. Same thing with y. Y isn't a great choice because equations 2 and 3 would be, with z, not y. Z would be kind of tough too. The equations 2 and 3 wouldn't be so bad, but when I want to pair either one of those equations with equation 1, that's not going to be very compatible, is it? Z's are going to be harder to eliminate. Pretty clearly in this case, y is my best choice, isn't it? Right? I could eliminate y from the top two equations easily, and then I could pick maybe the bottom two and eliminate y pretty easily, right? So there's my first step, is I've got to find a way to eliminate the same variable twice. That's steps 1 and 2, okay? So let's do that. So how about, first of all, if I want to use the top two equations, how could I eliminate y? Okay, the equation 2 I could multiply by 6, correct? Leave the top one alone and multiply the bottom one, or the middle one, by 6. So that's going to give me, am I recording? I think I am. Yeah, I am. 2x minus 6y plus 9z equals negative 8, and 30x plus 6y plus 12z equals 60. Okay, and if I add those up, sure enough, as I desired to do here, I got rid of the y's, and we get 32x plus 21z equals 52. Okay, so now what if we pick equations 2 and 3? How could I manage that? Negative 1 by either one. I'll keep the top one the same and multiply the bottom one by negative 1. So I'm getting 5x plus y plus 2z equals 10 and negative 3x minus y plus 8z equals 28. Add those up. The y's cancel. And I get 2x plus 10z equals 38. Okay. So I've got two equations in two unknowns. And so now I'm going to build a 2x2 system out of that and solve a little mini problem. You guys can do 2x2 systems in your sleep. That's no big deal. So that's going to give me the 2x2 system, 2x plus 10z equals 38 and 32x plus 21z equals 52. So which variable should I eliminate? X. Yeah, x. So what do I have to do to eliminate x?
Can you just multiply the whole thing by negative 1 on the top?
No. Negative 16, because I got to get opposite coefficients, right? So I'm going to need a 32x and a negative 32x, right? So we'll multiply top one through, now we'll just do this. Top one through by negative 16, bottom one we'll leave alone. That's going to give me negative 32x minus 160z equals 640 minus 32 is 608. And 32, yeah. And then on the bottom, I left it the same. 32x plus 21z equals 52. Okay, so if I add those up, look what happens. The x's cancel, right? Which is what I wanted. And I end up getting, what's that going to give me? Negative 139, is that right? Negative 139z equals 556, right? 556, right? Yeah, there we go. Okay. So if I divide both sides by negative 139, what do I get? Four. 4 is right. I get z equals 4. Okay. So what would I do? Now I'm solving a 2x2 system. So keep in mind, everything I'm doing down here is just to solve this 2x2 system, right? I'm not even worried about the 3x3 system. I'm just working on a sub-problem. A simpler sub-problem is solving the 2x2 system. So I got to find x. What do I do? Plug it in. So I'm going to plug into which of these equations? Top one for sure. Right, so we'll plug that in right there. And we're going to get 2x plus 40, just 40, right? I'm plugging in 4 for z. Plus 40 equals 38. So what's x equal? Negative 1. Good. Okay. Okay, give me thumbs so far. We good? Okay, now it's easy, right? Because I solved that collapsed 2x2 system, I know 2 of the 3 variables. How could I find the third variable? Yeah, go up and pick whichever one seems easiest, probably the top one or bottom one. I don't care. We'll use bottom one. Doesn't make any difference. So, oh, maybe it was the middle one. I probably picked the wrong one, but it doesn't really matter. So we'll plug into that middle one or the bottom one, just because I guess I can see it better. How about that? And what's that going to give me then? I'm going to get 3 times negative 1 plus y, which I don't know. minus 8 times 4 equals negative 28, right? So if I solve that thing, I'm getting negative 3 minus 32. So y minus 35 equals negative 28. So what does y equal? 7.
You could have did the middle one. It was so much easier.
Probably would have been. Okay, so how would I write my answer then?
You put parenthesis, negative 1, comma, 7, comma, 4, and parenthesis.
Good. And what do I call that thing? An ordered triple. There you go. It's an ordered triple. Okay. Okay, no big deal. So I'm not going to, for you guys, I'm not going to you can do this stuff. I might, if I have time, I'll go through and do another problem just so you can see another example, but I doubt I even need to. In fact, I'm even going to skip that. Let's just skip up to solving another one, but I want to see how you can tell if you get a weird answer, okay? So if we get an ordered triple, then it corresponds to a point in space, right? If I go back to this last solution that we had, what does this mean? Well, it just means that on the XYZ plane, I would start at the origin, I would go 1 to the left, 7 up, and 4 out of the board. And there's the point of intersection of those 3 planes, okay? So what about this one, though? Here's our system, okay? If this is an inconsistent system where there's no solution, what do you think has to happen? Like, what do you think is going to happen when I'm doing the algebra here? What always happens if there's no solution? Okay, variables cancel out, and I get what kind of an equation? Well, not y equals something. I get something that is false, like 2 equals 4 or something, right? So the variables, at some point, the variables should fall away, and I should get a nonsense equation that is false. And that tells me there is no solution, okay?
So is it possible that those variables would work for like 2 of them, but not once? You have to go put it into all of them?
It is. It depends, and it's just luck of the draw. You might, it's a very good question. So you could get this, like you could get this immediately, or it might take you a little bit longer to see it, okay? But you at some point in here, you're going to see that there's no solution. Okay, so what variable do you want to get rid of? Let's get rid of y. Okay, so you're going to use probably the bottom 2 equations, I'm guessing, to start with. So we'll get rid of y in the bottom 2. And that means I don't have to do anything to them, do I? So this one I'll just leave alone. I'll tell you what, I'm going to do this one. I'm going to do that part over here. So 2x plus y minus z equals 10 negative x minus y plus 4z equals 4. Add those up. The y's cancel. And I get x plus 3z equals 14, right? Okay. And so now what other 2 should I use if I want to eliminate y? Which one? I could do 1 and 2 if I want to. That's fine. So what am I going to multiply? Top one I'll leave alone. Middle one I'll multiply by. Okay, so if we do that, that's going to give me 5x plus 5y minus 20z equals 5. And this one I'm going to get negative 10x minus 5y plus 5z equals negative 50. Okay, and if I add those up, the y's cancel, and I get negative 5x minus 15z equals negative 45. And now I'll build a 2x2 system out of those 2 equations in x and z, right? And what's that give me then? I get x plus 3z equals 14 and negative 5x minus 15z equals negative 45. Okay, what? Multiply top one by 5, okay? So the x's will cancel then, right? So I get 5x plus 15y equals 70. Negative 5x minus 15y.
Why did you change it to?
Huh?
It's
Look
a
at
Z,
you
not a
put
Y.
Y's in the 15s.
Oh, you're right. What am I doing? I got so excited there. Sometimes they get really excited about these things, about, you know.
It's like
Why are we still here?
I'm just happy it's
Okay, and yeah, sure enough, look, the x's cancel, the z's cancel. So I get 0 equals 25, which is false.
not false. No, that's the truest statement I've ever seen in my life.
Okay.
It's false.
So if that's false, what's that telling us? If that's false,
No solution.
it's telling us, yeah, that this is inconsistent.
Well, it says solving with an inconsistent system.
Okay, so that worked fine. I'm going to show you. Here's how I would have done this one. Not that this is that big a deal, but I would have done this one a little bit faster. Here's how I would have done it a little bit faster. See if you guys can tell me why I'm choosing this. I would have definitely chosen. I would have chosen equations 1 and 3 right away. How come?
Times by 5, you'll get rid of the x's and the y's.
Okay.
And then you're left with 0 equals 1.
There you go, right? You see that? Because the ratios of the variables are consistent, right? The ratios of the terms. Everybody see that? So if we had left this one alone and multiplied this one by 5, oops. And look what happens when I add those up.
Everything cancels. And you're left, that's what I said.
Ah.
Right.
Why you said 0 equals 1.
Okay, so what's that mean? What's that mean then? What that means is this system has no solution. Why? Because these two planes are, the system of those two planes is inconsistent. But what's that mean about the two planes? They have no solution. So what must be true of those two planes? How are they oriented? So they're parallel. Yeah. Right? And so what do we have here then? If you kind of start to get a feel for this a little bit, which you probably are a little bit, we have two parallel planes and one plane that's non-parallel with those. So this plane intersects each of those separately, but there's no simultaneous intersection of all three. Okay? So there's no solution, right? Give me 1 to 5 on that. I'm just curious if anybody follows. Okay, so you get the idea, right? Okay. Okay, so what about this guy? So this time, I'm telling you what's going to happen. We're going to get a consistent, dependent system. So what's that mean? So we're going to get a consistent, dependent system means we're going to get an infinite number of solutions. Okay, so we're going to get an infinite number of solutions. Okay, so Deegan had an idea. What do you think here? Which variable, which two should I combine first? Because first of all, anticipate what's going to happen. If I get infinite solutions, what's going to happen to tell me that? How are the math gods going to tell me that? I'm going to get, okay, but what's going to be truth? So the variables drop out, and then I'm going to get an equation that is, 0 equals 0 or 4 equals 4, something like that, right? I'm going to get a true statement, okay? So, Deegan, which two would you choose to combine first? Okay, so you're going to use 1 and 3. Good choice. If I use 1 and 3, look what happens here. If I use 1 and 3, I can already see.
whoa. We solved that 2 minutes ago.
Okay, I'm going to multiply this one by 4, right? Not -4, by 4.
Yeah, not negative.
And I get 12x minus 16y plus z equals z, plus 4z, sorry. Oh, whoops. Oh, I hit that, didn't I? Come on.
It's right there.
Oh, there it is. Okay. And this guy,
It's a negative 12x.
thanks. So what do I get when I add those up? 0 equals 0. Okay, okay, now listen. Now, what does that tell me about planes 1 and 3? They're the same plane. Okay? They're the same plane, right? So if they're the same plane, it doesn't matter what this plane is, it's going to intersect. These planes overlap. I know that when they intersect, I'm going to get a line as my solution set, right? Everybody agree with that?
Yes.
Okay. Okay, so the answer is it's consistent dependent, but we can do better, right? We can do better than that. We could do more than just saying, I know there's an infinite number of solutions. We could even figure out what those solutions look like, because the solution set is a line, right? So we should be able to come up with the equation of that line in three-dimensional space that represents the infinite solution set. Okay, that's useful knowledge. It can be, like if this is modeling something physical, we'd want to know what that solution set looks like, for example. Okay, how could we do that? Well, we'd have to go back to the drawing board, because that didn't help very much. All that told us was that these two planes were the same. So I'd have to go back and find the intersection of this other line with one of the planes to see what the line is, right? So let's pick equations 1 and 2, and let's eliminate a different variable. Let's not eliminate z. Okay, let's eliminate, for example, how about if I eliminate x? Okay, that's fine. So if I eliminate x in these first two, I'm going to leave this one alone, and I'm going to multiply this one by -3. Right? So look what that does. That gives me 3x. Okay, you got to watch this. This is really cool math. I mean, I know this is way above anything you've ever done, but you're starting to see something real here a little bit, right? So you get 3x minus 4y plus z equals 0. Hey, don't listen. That one's -3x minus 3y equals 0. Okay, and if I add those up, the x's cancel, and look what happens. I get -7y plus z equals 0. Okay? Okay, we'll just leave that one there for a second. So now what if I try to eliminate a different variable? What if I go back? I could pick these two equations if I want to, it's fine. Or I could pick the first two again and just eliminate a different variable. These are the same plane after all, right? They overlapped, we already know that. Okay, so I could pick either one. How about if I just pick the top two, being as that's a little bit simpler. Instead of this one and this one, I'll just pick the top two. And I'm gonna leave the top one alone. Top one I'm gonna leave as 3x minus 4y plus z equals 0. And if I want the y's to cancel, what would I multiply the second one by? By 4. Good. Okay, so I'll multiply this one by 4, and I get 4x plus 4y equals 0. Add those up. The y's cancel, and I get 7x plus z equals 0. Okay, now what's common in both of those is z, right? I end up with y being related to z and x being related to z. So here's how I could write this solution. I could say, okay, if I solve for y up here, I get y equals 1/7 z. Okay, that tells me, that's important. That tells me that whatever value z is, y is always going to be 1/7 of z. So if I pick z to be 70, I know y is 10. The y coordinate is 10, guaranteed. What does this one tell me? If I solve for x, I get x equals negative 1/7 z. So again, I know if I choose a value of z randomly, I know what the corresponding x and y values would be. So I can predict what any ordered triple is going to be based on the value of z, right? How about that? So I could actually write my ordered triple in this form. That's it. So look what that says. Z could be any real number, but whatever value I pick for z, it predicts the values of x and y. Well, doesn't that mean, isn't that what a line or a plane does, right? I mean, in this case, it's a line. In this case, it's a line, right? This is just going to give me, if I were to graph this thing, and we don't really need to look at the graph of this for now. That's probably going a little further than we need to. But can you just picture this in your mind here? If I picked a collection, like if I wanted to plot that line in three-dimensional space, all I'd have to do is pick a couple points and then connect and extend, right? So I could pick a value like, let's just pick z equals 0. If z is 0, I get the ordered pair. I get the ordered triple, 0, 0, 0. So it's on the origin, right? If I pick a different value of z, like what if I pick 7? That's going to give me negative 1, 1, 7. Connect those 2 points in space, and that's my line. How about that? Yeah, doesn't it? Right? So if I pick 14, I would get negative 2, 2, and 14, right? Everybody get that? Yes.
Are we going to have any of these on homework?
Yeah. Yeah, no, you get homework's starting tonight on this. So, but what would, okay, so listen though, what would I expect? What would I expect on the homework? We'll look at a quick example. All I would ask you to be able to do is say, okay, like what's the ordered triple like that? Okay, if it's consistent and dependent. Okay, but you're also going to have access. We're not done yet. I'm going to show you something really cool here. Okay, here is the silver bullet. This is the way that we can solve all these very, very quickly. Okay, so right. So now this is written a little goofy. So this is a 4-dimensional system, right? 4x4 system. So graphing this would be a problem because you could only understand what the graphs would look like in a 4-dimensional universe, which we don't have, right? So there's a x-axis, y-axis, z-axis, and w-axis, which is who knows where, right? It's non-physical for us because our universe doesn't support another orthogonal dimension. Okay, but it doesn't mean you can't solve the system. It's no big deal to solve a 4x4 linear system. The solution is going to be meaningful to us because it's going to be the values, the ordered quadruple, right, which is going to be the values of x, y, z, and w that make each of those equations true. Okay, this does not have to be, you don't have to think about this in terms of a graph. Did we have to graph this last example to get solutions? No, we didn't, right? It turns out, or how about if we go back to this one? Right, with this one, we got a single ordered triple. Sure, if I wanted to graph that in 3 space, it corresponds to a point, but we don't need to do that. We just found those are the values of x, y, and z that satisfy the original system, right? What if, so same thing's going on here with a 4x4 system. These might represent, this could be something like an application where X is the price of a chair, Y is the price of a sofa, Z is the price of a refrigerator, W is the price of an oven. And we're saying that certain combinations of different numbers of each of those appliances would cost a certain amount of money. If I had 4 examples, that just amounts to a 4x4 linear system. If you gave me 4 combinations of those different appliances and furniture, and the total value we could easily just solve for what the value, how much each one of them cost, right? So we don't necessarily need to graph this in 4-dimensional space. We just solve the system and it has meaning, right? Okay, so how do we do this? Well, we could do this algebraically. You guys could, it'd take you a while. But let's do this with technology. So bust out your Chromebooks, go to Desmos, and I'll show you on there next, but I'm gonna do Desmos first. Okay, and then be quiet, please, because I want to explain something to you. Okay, so what we got to do is we have to build a matrix that represents this system. What is a matrix? A matrix is just an arrangement of numbers. That's it. Okay. Yes, sir. You're not going to go to either one. So just I'll tell you how to get there in a second. But first of all, let's build this matrix before we jump into Desmos. So what I want to do is I want to turn each of these equations into a row in my matrix. To do that, I have to make sure that each linear equation is written in standard form, which means the variables have to be in alphabetical increasing order. Okay, the W is out of place. People do this different ways. You could put the W before the X is what I would probably do, honestly, because it's alphabetical. But as long as you're consistent, it doesn't matter. As long as we're going to always be the same and say we're going to write the variables in the order X, Y, Z, W equals the constant. As long as it's all the same format, it's going to be fine. So then we're going to allocate the first column. These are the coefficients of X. These are going to be the coefficients of Y. These are the coefficients of Z. These are the coefficients of W. And those are the constants. Okay? So how would I say that first row then in a matrix? What's the coefficient of X in the first equation? Well, what's the coefficient? 1, 1. What's the next one? 1, 1, 1, 6. There's the first row. Second row. 0. Because there's no W, right? Okay. Next. Okay. Next.
Slow down. You guys are monsters.
Okay, so that's matrix A, right? That's what's called an augmented matrix. Normally matrices, well, okay, so an augmented matrix means that we're going to include not just the coefficient columns, but also the constant column. Sometimes you'll see that with a little vertical bar separating like an equal sign, which just represents an equal sign. I mean, both ways. Either way, you might see it one way, you might see it the other. They mean the same thing. So here's how you do this in Desmos. So first of all, I know you guys think you're always going to use Desmos Scientific, but it turns out you're not. And so what I would do right away is I would bookmark this page. I would bookmark desmos.com. So when you get there, you always, hang on here. When you get here, you have the option of which Desmos calculator you want. And in this case, the one that we want is the matrix calculator. Okay. So click the matrix calculator and it takes you to here. Okay. So what I want to do is I want to build a new matrix. So everybody watch, please. I click the new matrix button and I have to tell it the size of the matrix. How many rows do I have in this matrix? 4. How many columns? 5. Good. So there's my matrix. And I'm just going to build a matrix that has these rows. Now, here's how you enter this. Listen, because there's an easy way and a hard way to do this. You always use the right arrow. So I go 1, right, 1, right, 1, right, 6, right. Oops, hang on, I missed one. 1, 1, 1, 1. And then when I get to the 6, I hit the right arrow again, and it advances me to the next row. Okay, everybody get that? So then 2, negative 1, 1, 0, 1. 3, 2, 1, negative 1, 11. 1, negative 2, negative 2, 2, negative 2. Okay, everybody agree? And then once I've got that in there, I hit enter. I hit this blue button and it stores that matrix. Okay, and so it looks like everybody should now look like this. right? That's the matrix that we just built. Okay, now what? Now you're going to do a bunch of fancy row operations all at one time. This is stuff you will learn in college. If you're going to study engineering or physics or math or statistics or maybe even like chemistry or something, you probably would learn this. To chemistry, you definitely would. I don't know if you would for biology or other stuff, but for any of those majors, you would. Linear algebra is just the mathematics, the algebra of solving great big linear systems using all these row operations in matrices. Okay, there's a whole bunch of row operations we would need to use to get this solution, but Desmos will do it all at once if you choose reduced row echelon form. Reduced row echelon form is going to rewrite that system as a single matrix that gives you the solution. So here's how you do it. You go RREF for matrix A, which is what we defined, and then there's the answer. Okay, now let's look at that answer and see what that represents. Okay, there's what it gave us for our solution. Okay, what does that first row tell us?
X equals 1.
X equals,
W equals 0.
no, what's the first one tell us? No, not X equals 1. No, it tells it, go ahead.
The coefficient of X is 1.
Yeah, so 1x equals 2. Well, what's 1x is just x, right? So this is telling us x equals 2. How about that? What's the second row tell us? Y equals 3. What's the third row tell us? You mean z equals 0? What's the fourth row tell us? How about that? Isn't that cool? So then that as an ordered quadruple, that just tells us it's 2, 3, 0, 1. And so that point in 4 space would be 2 to the right, 3 up, out of the board 0, and 1 into the fourth dimension, whatever that would be, right? Okay? It's so useful. This is so useful. Oh my gosh. I bet I've used these things. I'm not kidding. In my career as an electrical engineer, I bet I used these things 1,000 times, maybe 10,000 times. In college, I mean, you use this stuff all the time when you're doing math. All the time. This is so useful. Okay, so what happens? Let's see what happens here. How could we tell that we're going to get an inconsistent system? So if I did the same stuff with this, right? If I set up a matrix A, corresponding to this system, right? 3 by 3 matrix, and I did reduced row echelon form of matrix A, this is what I would get, okay? And we don't have to go through the whole process. You guys will get plenty of practice with that. But interpret this for me. What's important here if I look at those solutions? Okay, but even more than that, look at the bottom row. Now notice that this is not giving me a solution. If I go back, a single solution, if I go back to the last solution, look what we get. If you look at I want you to look at something here. If I look at the first square part of that matrix, you see what that looks like? That's called the identity matrix. This is the matrix equivalent of the number 1. If I multiply this matrix times any compatible matrix, it's going to leave it the same. But more importantly, what it's telling us is that it's giving me solutions for X, Y, Z, and W. If I don't see that look where I get a descending diagonal of 1s and the rest are 0s, then I know it's an oddball solution, right? Like this one. Oops, like this one. Look what happened. I don't get 1, 0, 0. I don't get that. So then I just immediately go down to the last row and I look at the last row because that's going to tell me something important. What does the last row say? 0 equals 1. False, right? So that means it is inconsistent, right? No solutions. Okay, how about this one? If I do the same thing again, only this time, look what I get here. Okay, and this is the same one we did a little bit ago. And we got that weird line, and right, we got that infinite solution that was a line. Look how easy it is here. Look how quick that would have been. What does this bottom row tell us? I know I got a weird one because that's not the identity matrix. So the bottom one tells me 0 equals 0. So infinite solutions, but then I can work up to the other rows and look what they tell me. This one right here tells me x plus 1/7 z equals 0. Huh, that's familiar, right? What does this middle one tell me? Y minus 1/7 z equals 0. Well, isn't that just giving me, let's see, this one right here? No, no, it's that one. It's giving me that, isn't it? Right? It's giving me that answer right there, right? I didn't do anything, but you get the idea? Okay. Oh, it's a lot of stuff, huh?
That's cool though.
That's honestly a lot.
I guess I was reading it right. I was reading